Alright, so this question is quite a bit more complicated than the previous question. This is our target equation, and we need to make this target equation based on from the reactions listed below. Almost always we're going to use all of the equations below. Sometimes they'll have some extra ones, but it's not very common. First thing that we're going to do is we're going to identify the chemicals that are in the target equation and where they are in the equations that we're going to use. So here we have hydrazine here. We have hydrazine and we have hydrazine. We have it in two different equations. At this point, it's probably not a good idea to start with that equation. Or pardon me, to start with hydrazine. We have oxygen here, and we have half an oxygen here and half an oxygen there. Don't worry about the fractions. Fractions will look after themselves. But again, the oxygen occurs in two different equations, so probably not a good idea to start with that. We have nitrogen. Nitrogen occurs in this equation, and it doesn't occur in any others. So that's a good candidate to start with. And then finally, we have water. Water's here, water's here, water's here, water is here, and water is there. Now, if that tells us anything, it says do not start with water. Now you'll notice something else. Our target equation, we need to have one nitrogen, but the thermochemical equation that we have at the end has 4 nitrogens. Now you could multiply by 1/4, or I suppose divide that equation by 4, but you're going to end up with a whole lot of fractions, and you probably don't want to deal with those fractions. We can save it to the end, and we can divide by 4 at the end, and hopefully avoid as many fractions as we can. So let's start off. We're going to write down that target, or that equation, the first equation here, and we don't need to multiply it by anything. So we're just going to multiply it by 1. Okay. So we have 2 NH3s, 3 N2Os, gives us 4 N2s and 3 H2Os, and our delta H, I'll make that a delta H, is equal to negative 1010 kilojoules per mole. Okay. Now, let's start getting rid of things that we don't need. What do I mean by that? Well, NH3 is not in our target equation. So if ammonia is not in our target equation, we don't want it. So we're going to try and get rid of it any way that we can. Now fortunately, it occurs in our third reaction here. Now it occurs in our third reaction, however, it's on the product side, on the reactant side. We need it to be on the product side. So we can multiply by -1. If we multiply by -1, that reverses the equation, and it also changes the sign of the delta H. So this is going to end up looking like this. We're going to have 2 NH3s. We're going to have half an oxygen. And on this side, we're going to have N2H4. And we're going to have an H2O. And because we've changed the sign, we've reversed the direction, so we end up changing the sign, 143 kilojoules per mole. And we have cancelled our ammonia molecules. Okay. Now another thing that we need to cancel, something that isn't in our overall reaction, in our target equation, are these 3 N2O molecules. Those 3 N2O molecules are in that reaction there, but again, they're reactants. We need them to be products so that we can cancel it out, and we need to have 3 of them, so we're going to multiply by -3. So let's take a look at how this is going to turn out. We're going to have 3 N2Os. We're going to have 9 hydrogens. On this side of the equation, we're going to have 3 H2Os, and we're going to have 3 N2H4s, and we have to multiply our 317 by 3, so 317 times 3 gives us 951, and the sign changes, so that's delta H is equal to positive 951 kilojoules per mole. So that allows us to cancel out our 3 N2Os. Now at the same time, we have 3 water molecules that cancel out with 3 water molecules, so that's not too bad. And let's see where we are. We have 9 hydrogens that we need to cancel out, and in this equation here we have 1 hydrogen, and it's a reactant just where we need it to be, but we need to have 9 of them, so we're going to multiply by 9. So we're going to have 9 H2s, and we're going to have 4.5 oxygens, and we're going to have 9 H2Os, and our delta H, we're going to have to multiply that by 9, so 286 times 9 gives us 2574 kilojoules, and it's negative 2574 kilojoules per mole. And let's see where we end up. Okay, we have 9 hydrogens, cancels with 9 hydrogens, life is pretty good. We have half an oxygen, which will cancel nicely with that half of an oxygen. We have 9 H2Os, but we still have an H2O right here, so we can cancel that 9 and turn it into an 8. And it doesn't look like anything else is going to cancel, so let's total up our reaction. So we have, let's use a nice color, let's use, oh, a nice little pink. So we have 1 hydrazine and 3 hydrazines, so that's 4 hydrazines, 4 N2H4s. We have 4 oxygens, there they are right there, and we're going to have 4 N2s and 8 H2Os. And our total delta H is going to be 1010 negative plus 143 plus 951 plus a negative 2574 gives us a delta H of negative 2490 kilojoules per mole. Now, of course, this isn't quite the reaction we want. We need to divide everything by 4. So we have N2H4 plus O2 gives us N2 plus 2 H2Os, and our delta H, we're going to divide that by 4. Gives us negative 622.5 kilojoules per mole. So what that says is that for every mole of hydrazine that we burn, we get 622 kilojoules. For every mole of oxygen that we use to burn, we get 622 kilojoules. For every mole of nitrogen that we produce, we get 622 kilojoules, and for every 2 moles of water that we produce, we get 622.5 kilojoules per mole.